Okay, we're looking at 10.1 parametric formulas, and we're going to be looking at the derivatives, so the differentiation formulas for deriving parametric equations. And so if both x of t and y of t are differentiable, and dx dt does not equal 0, then we can say that dy dx equals dy dt over dx dt. This makes sense because dy dx, of course, is just the change in y over time, divided by the change in x over time. So this, I think, is pretty intuitive. But also, if you look here in the highlighted part, it comes also straightforward from the chain rule. If you're taking d dx of y of t, well, that's going to be dy dt times dt dx is how you would do the chain rule, because y is a function of t. And so if you just divide by the reciprocal, you'd, of course, get dy dt over dx dt. So we should be pretty ready to accept that. So then let's just say, though, that after we do dy dt over dx dt, that we accept that as y prime. So now the question is, if we want y double prime, we're just going to say that that's d dx of y prime. And of course, you can see them alluding to that here. And the key to this is just think of y prime as some other function. It's just a new function. And so what do you do with any function, y of t, and you want to take the derivative with respect to x? For parametric, you do dy dt divided by dx dt. And so all you have to do is simply take dy prime dt and divide by dx dt again. Some people will say, well, why don't we divide by dx squared dt? Or why don't we just take the derivative of the y twice? And it's because after we get this first derivative, y prime, we're essentially starting over. Now we just have y prime of t and x of t. And so how do you take the derivative of y prime of t? With respect to x, dy prime dt over dx dt. And so now that we have that solidified, we can go ahead and just do an example problem. And for this example problem in the book, there's some confusion because it looks like this square root goes all the way over the t. We're going to act like it doesn't. We're going to act like it ends just before, and only this square root of 3 has it there. And so let's go ahead and find the first derivative. So dy dt over dx dt. So the first derivative is going to be just the square root of 3 over, and then dx dt. We have the negative. We bring down the 1/2, so we have negative 1/2 of t plus 1 to the negative 1/2. And then chain rule would just be times 1 for the derivative on the t, so we don't need any chain rule action here. And so let's just go ahead and simplify that. So we're going to have negative 2 radical 3, and then, of course, times t plus 1 to the 1/2, which is just radical 3. But let's just keep the square root of t plus 1. But let's just keep this as a constant out front. And, of course, this is equal to, we could even think of this as y prime, right? But that is our dy dt. And so now, if we want to find the second derivative, right? If we want to find the second derivative, then we just need to do dy prime dt over dx dt. And so dy prime dt is going to be the derivative of this with respect to t. So we're going to have negative 2 radical 3 over 2, because times the 1/2, times t plus 1 to the negative 1/2, all over, and then dx dt is again going to be this same thing that it was before, and so let's put that in the denominator, negative 1/2 t plus 1 to the negative 1/2. Interestingly enough here, it's kind of crazy to think of, but this just cancels here. The negatives cancel. This 1/2 and this 1/2 cancel. And so you end up with just 2 radical 3 for your answer, interestingly enough, which is kind of crazy to think about. But as long as our math is correct there, we've got it. And again, the key point to this is just that when you get this y prime, this dy dt, this is just another new function of y of t. And so you take its derivative the same way. Constantly, you're just always dividing by this dx dt when taking derivatives with parametric functions.